create aldehydes, ketones, whereas alkynes give us carboxylic acids, period. Everybody okay? So let's try this out a few times. Oh, by the way, what if it were what will be the outcome, anybody? So do you agree that this will break apart? Right?
Yes.
So what does that become? Right?
Mm-hmm.
But I'm more curious about this part. When you have a terminal alkyne, this part of the terminal alkyne actually becomes, what is that? Anyone? What is this?
Carbonic acid.
It is carbonic acid, H2CO3. And what happens to carbonic acid as soon as it's created? What happens
It breaks
to it?
into H2O and CO2.
As you've seen before in lab also, we've talked about this, right? So the products will be basically this benzoic acid plus water and CO2, because carbonic acid doesn't survive, it automatically breaks apart into that. Okay, just like that. Okay, let's try this a few times. So, same reagents, I'm just not.
Is there less light?
No, wasn't all this. Oh, light. I thought you meant like HU over there. Doesn't it need light? No, what else? Okay. Not wrong. What?
Maybe it's this one over here.
No, there should be the same. There we go. It has switches both sides. Okay, please go ahead. Tell me what will. Let's do this quick, guys. Same reagents. Feel free to come to the board and draw them. I'm going to very soon get bored by seeing dash up here all the time. Come on. Let's. Okay, good. See that. The terminal one becomes carbonic acid, which breaks apart to become water and CO2. Great. Now. Do you all agree?
Maybe. Miscounted my carbons.
1, 2, 3, 4, 5, 6, 7, 8, 9,
1,
10,
2,
11, 12. No, it looks good.
3, 4, 5, 6, 7, 8, 9,
Do
10,
you all agree,
11,
guys?
12.
Please notice alkenes only becomes aldehydes and ketones. The alkynes become carboxylic acids. You guys see that? So can we go backwards?
3, 4.
If you're given the products, can you tell me what was the original reactant? So given the ozonolysis products, please give me the original reactant. Alkenes become aldehydes, ketones upon ozonolysis, whereas alkynes become carboxylic acids. So using that, can we try not use green, guys? For some reason, the green does not erase very well. Oh, this one did. Why did that one not?
Permanent? Or it's a different one.
Yeah, it's a different brand, so which is the good one? Yes, can we please write some answers on the board?
Just do it.
Maybe we should institute extra credit for going to the board.
Oh, dude, that would be incredible.
It's like taking me so long to do it.
Alkenes become aldehydes, ketones, alkynes become carboxylic acids.
aldehydes become ketones and what?
Alkenes become aldehydes and ketones. And alkynes become carboxylic acids.
Oh, am I missing something in the first
Yeah.
one?
Yeah, because there's 3.
Yeah, you're right.
Okay.
I'm trying to figure out how this works.
Alkenes become aldehydes and ketones.
Oh, yes, I am missing.
I just was thinking it might be a carboxylic acid.
Yeah, but I'm missing that. You're right. I'm missing something here. Acetic acid. Yeah. Acetic acid. Are you sure? No.
These ones aren't OHs, right? So they wouldn't have the same.
Yeah, but then it did ozonolize. It's an aldehyde or a ketone. So what must they be?
Oh, that's fine.
You know, you're right about the alkyne part. You're right. Carboxylic acid be alkyne. What about those?
That's a fun question.
Did you say it's a funny
I
question?
said it's a fun question.
It is, yeah.
It's ketone.
So alkenes, when they ozonolize, they become aldehydes, ketones. Alkynes become carboxylic acids. So wherever there are carboxylic acids, they must have come from an alkyne. Wherever there are aldehydes, ketones, they must have come from an alkene. Isn't that right? Alkenes break apart to make aldehydes, ketones. So we have to think backwards now. Do you agree with what Dash has on the board?
That's weird.
If Dash, well, that's just because of the drawing, but
Okay.
do you agree with what he has? So the point is, well, notice here's an aldehyde and a ketone, isn't that right?
Yep.
So those two carbons must have been what? Connected to each other, being part of what?
A
ring.
And what functional group?
alkene.
Alkene. Isn't that right?
Yep.
Isn't that right, everybody?
Yes.
So if you, I'm just numbering to keep track 1, 2, 3, 4, 5. So what is that? That's a cyclopentene. Cyclopentene, if you take those two ends and put them together. Agreed? Everybody? But then wherever there is a carboxylic acid, that must have come from alkyne, which means that these carbons were connected to each other through a triple bond, a carbon-carbon triple bond, an alkyne. So it's the same thing, you're just going backwards. If this bond breaks, you get the aldehydes, ketones. When this bond breaks, you get a carboxylic acid here and a carboxylic acid there. Does everybody see that? Everyone okay? I don't know if silence means yes or no.
Oh, yeah.
No, that's just you. What about the rest of you?
Yeah.
Okay, so you have to go backwards. If I took these two carbons, do you all recognize that's an aldehyde? That's point number 1.
Yeah.
Yeah.
Do you all recognize that's a ketone?
Yes.
So, what functional group gives us aldehydes, ketones after ozonolysis?
Alkenes.
An alkene. Which means these two carbons, 1 and 5, must be the original alkene. Would that then look like that? Isn't that right? Agreed?
Yes.
Say something.
Yes.
I agree.
When nobody says anything, just stares at the board, I have zero idea what that means. And then, these two must have come from the original alkyne. So, that carbon is right here, and that carbon is right here. Gives us that. Do you all see that?
Yep.
So you're working backwards. I gave you a broken toy, you got to put it back into pieces, knowing where it came from. Okay, then let's do the same here. These are all carboxylic acids, notice. All the functional groups in the products are carboxylic acids. So there might be
4.
suggestions? Cyclo. Well, oh, so you're connecting this to each other? Then where will they go? Oh, did you say butene?
I didn't say.
Someone said something. I heard the sound from there. Yes, but again,
1, 2.
what product do we get from alkenes when they are ozonalized? When alkenes are ozonalized, alkene is a double bond. When it undergoes ozonolysis, what do you get?
Aldehydes, ketones.
Aldehydes and ketones. Do you all remember that? Isn't that right? Agreed? What about alkynes? What do they give us?
Carboxylic acids.
So, in that example, are the
Carbonic.
products, guys, can we do this please? Are these aldehydes, ketones, or carboxylic acids?
Carboxylic
If we
acids.
are having trouble recognizing functional groups, you've got to go back. This is high time. We need to know what are aldehydes, what are ketones, what are amines, what are alcohols, blah, 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 blah. So, do you all agree that these are carboxylic acids?
Oh,
Yep.
that's no
So,
doubt.
what are they coming from? Are they coming from alkenes or alkynes?
Alkynes.
So what's the reactant? Take those pieces, put them together. Where are you going to go there? And then in the bottom example, what is this? An
Aldehyde.
ketone, carboxylic acid.
Aldehyde,
How about this?
ketone,
How about this?
carboxylic,
acid. Carboxylic
carboxylic.
acid.
So what functional group do aldehydes, ketones come from?
Double bonds.
alkenes,
What functional groups do carboxylic acids come from?
Alkynes.
You just have to put them together. That's it. Yes.
So for the first question,
Yes.
they're all carboxylic groups.
Right.
And it doesn't matter because the main one is symmetrical.
Yes.
But
If it weren't, you can have both.
you have multiple products.
Exactly. Or multiple reactants possible.
Okay.
Yeah, absolutely.
Probably.
You have an extra carbon somewhere.
Isn't there 10 carbons?
Where's your carbon?
1, 2, 3,
Maybe we should do
4,
what
5,
Camilla
6,
is
7,
doing, is
8,
numbering the
9.
carbons and see if that
10.
makes sense.
Mm-hmm.
So,
Number over here.
yeah, please do. You'll notice that 3
1,
doesn't
2,
match.
3.
Yeah.
Go ahead, you'll figure it out. Once you start numbering
1,
the carbons,
2, 3.
you'll see it yourself.
4,
There you go.
There you go.
Notice
1,
where's your
2.
triple bond?
Oh.
4 plus 3 is 7 plus 2
Where
is
should
9.
we-
Take out between 3 and 4.
Come over, help her out. It's okay.
No, you're good. Just take out 3 and 4. I thought she was in there.
You can go.
No, she's
Oh.
helping her.
Are you going to jump in the fray? Is there a key for this on Canvas?
Let me see.
The worksheet I gave you guys last time. Is there a key for that?
I think so. I'll check.
Sometimes numbering your carbons really helps, as you might notice in some of your answers to the test. Guys, keep track of your carbons. Otherwise, I'll destroy.
No, we-
Okay, while they're figuring it out, and anybody can come up and help them out. Come on, don't just let them stumble through the choices. If you were like, oh, come on, what about this? Go ahead, tell them. Thank you, though. Is it? Is it there? Oh, you.
I went to
I just-
chemistry 261.
Oh, I
But
see.
here it is.
Oh, you can
Oh.
still see chemistry 260.
Yeah, even 140.
How come? I thought that they close after the quarters? Oh shoot, maybe I need to go change that.
Is
Oh,
it this one?
open it, let's see, let's take it. What does that look
Oh,
like?
this is alkenes.
Alkenes, no, alkynes, yeah.
Alkynes.
Let me know. It's right. Okay, ooh. Okay, so the only thing I would suggest, because it's a little unclear here, is that carbon the one that's making the triple bond, or is there a separate carbon there?
Separate.
Okay, so let's just make that very clear, because they are so close to each other, it becomes a little difficult to comprehend that. Does that make sense? So 1, 2, 3, 4, 5, 6. So same thing
Triple
here.
bonds don't make angular
Yeah,
bonds.
but again, that's what they're trying to say is those are two separate carbons, right? So can we just elongate it enough so that there is no confusion about that? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Does everybody agree? Everybody okay with that? Okay, and here, this is the other one. So aldehydes, ketones come from alkenes. And then carboxylic acids come from alkynes. Everybody okay?
You
Is
got
it
it.
there?
Yeah.
The whole thing?
Oh, I don't know if the whole
Could
thing,
you
but-
just scroll
Yeah,
through
I'll
and just
scroll
make sure I have the whole? Guys, is that okay, everybody?
Yes.
Questions? Okay, the last two reactions of alkynes are really not very useful, but I think they're worth mentioning. So, but they're really not useful in synthesis. I forgot the number. What number was this? 5?
4.
4.
Yeah, it was number 4.
So 5 then?
Yes.
Okay, halogenation of alkynes. Synthetically, absolutely not useful. It's more of an FYI kind of thing. Alkynes react with halogens in just the same way as alkene did. By the way, how many X2s will be needed to add to a triple bond?
2.
2, because there are 2 pi bonds, right? So you need a minimum of 2 equivalents of those. Of course, you can take extra. So what would the product be, anybody? This is 1x2, right? Added across anti with respect to each other, as you would expect. Here's the other
A
x2.
tetrahalide.
What are we even going to do with that? Nothing. So it's really a more of an FYI kind of a reaction, synthetically not really very useful. Everybody okay? Okay, so I'm just leaving it because it's not really very useful. The last reaction of alkynes is hydrohalogenation, meaning we are adding hydrohalogen across the triple bond. And once again, how many equivalents of HX do you think will add across the triple bond? How
2.
many HXs would we need to add across the triple bond?
2.
Because there are 2 pi bonds, right? Now this goes through Markov-Nikovs only. Mechanism not necessary, mechanism not necessary for this either, but it does go through follows Mark's rule. So where would the hydrogen go and where would the halogen go? Anybody? If it's following Markov-Nikovs rule, where would the hydrogen go and where would the halogen go?
Halogen.
The halogen would go to the carbon.
And more substitute.
That
Which
one.
is which one?
The left one.
And hydrogens will go here. Exactly. You end up with a geminal dihalide, so to speak. But again, what are we really going to do with this? What's the purpose of a geminal dihalide or a vicinal dihalide? What is really the purpose of that? Anyone? As we learned on Monday, is to actually make an alkyne. So what synthetically there is no use of this reaction because the only purpose of these guys is to create an Make sense, everyone?
Yeah.
So these reactions are more FYI, these two, because synthetically they're not that important, they're not that significant, but more of, oh, same thing as alkenes. Guys, any questions about that?
Can you repeat the purpose of geminal is to make an
Alkyne.
alkyne?
As we
Okay.
learned on Monday, right? Synthesis of alkynes is from either a vicinal dihalide or a geminal dihalide.
Thank you.
So that's basically it. So when it comes to alkynes, let's summarize everything and and see what we've learned about alkynes. First of all, can somebody tell me what do we make alkynes from? Anybody?
That,
Monday.
No, sorry.
you have either 2 hydrogen and 2 halogen.
Let's use terms that we have learned.
Dehydrating?
Dehydration. Did you say dehydration?
Yeah.
Removing water?
Keto.
Dehalogenation.
Oh.
Okay, so what do we use to dehalogenate and create an alkyne?
NH2.
That's the base, that's the
NaNH2.
reagent. What's the reactant?
Oh,
A vicinal dihalide. Of course, we can also use what? A geminal dihalide. Does that ring a bell, guys? This was Monday. What's the reagent needed to convert these into alkyne?
NH2 minus.
NaNH2, NH2 minus, absolutely. But please remember, if it's a terminal alkyne, how much, by the way, sorry, I'm losing my words here. How many equivalents of the base are needed to convert one of these into the alkyne?
3.
For the internal one, for a normal one, how many do we need? 2.
2.
Right? Because you're doing 2 eliminations. But if it's a terminal alkyne, then you would need 3, right? Or just take excess, meaning as lots of it. But then if it's a terminal alkyne, what must we do after step 1?
Hydronium.
Coordinated.
This is 2 steps needed for terminal alkyne, because terminal alkynes can easily be deprotonated with sodium amide. Does that ring a bell? Where do we get this from, anybody? Where does that come from? Quickly, guys.
Alkene.
Alkenes. And using what?
2 halogens and CH.
You mean X2 or 2X2?
X2.
X2.
So that's not the same as 2 halogens.
X,
Halogen itself is X2, right?
X2 and CH.
Solvent, most likely dimethyl chloride, or excuse me, methylene chloride. Does that sound okay, everybody? Yes? Okay, ooh, wrote it in the wrong place. Can I write it here? Sorry, I'm going to write this here. Okay, what about the reactions of alkynes? So, can alkynes be converted into alkenes?
Yes.
Using what?
H2 and
H2 Lindlar's catalyst to get us.
Hydrogen with Lindlar's catalyst to get a what? Come on, guys.
Alkene.
quickly.
Cis alkene.
The alkene.
To the what?
For the Z alkene.
Z alkene, exactly.
Z
Z
alkene.
alkene or the cis alkene.
And
Sodium or lithium
and
liquid
trans
NH3
and
for the
NABH4 and
For the
E alkene.
E alkene. Good. Okay. What else have we learned? We also learned that alkynes can be deprotonated, convert if it's a terminal alkyne. Only for terminal alkynes you can deprotonate the terminal alkyne, right? Using what? Using
NaNH2.
amide. Agree?
Mm-hmm.
What's the purpose of this guy?
Good nuclear power.
So what can we do with that guy? If it's a good
SN2?
Substitute.
SN2. So if you react it with R prime X, whatever the leaving group is, it does SN2 and creates a bigger alkyne. Isn't that right, guys?
Yep.
Did we learn this? Yes. Okay. What can we convert an alkyne into an alkane? Yes?
Yep.
Using what?
X excess H2
Uh-huh.
and nickel, platinum, or palladium.
Choose one, guys. Don't give me all three. I just need just for you to know that there
platinum.
are three possibilities. When you're writing your answer, just pick one.
Platinum.
Everybody, yeah, so I'm writing all for you to know. Everybody okay? Can we hydrate an alkyne? Meaning add water? Yes? What are the two ways in which we could do so? And what are the outcomes? What's the outcome if I were to hydrate an alkyne with water, sulfuric acid, and mercuric sulfate? What's the outcome?
You get double bond.
Louder. What do we get if you are adding water to an alkyne under acidic conditions?
A ketone.
A ketone. It goes through Markov-Nikov's hydration, makes an enol. The enol tautomerizes, and that mechanism you need to know to produce a ketone. Right? Everybody?
Mm-hmm.
But if you were to do anti-Markov-Nikov hydration, what's the outcome? A ketone or what?
Aldehyde.
An aldehyde, because it goes through an anti-Markov-Nikov and then gives you an aldehyde. But can I make this from an internal alkyne? Is that possible? Is it possible to get an aldehyde from an alkyne that's inside the chain? Can this make an aldehyde? Yes, no, maybe. Where is the double bond oxygen going to go? Is it going to go here or here? Can it go anywhere else? Guys, your blank stares are really scaring me today. It's like, oh wow, everything we did on Monday is already gone. How are we supposed to progress? We're already behind, as we know. This was done on Monday. Do you guys remember this? Show of hands if you went back on Monday and read the chapter. Show of hands if you went back on Monday and did some examples. Okay, I get it, but Tuesday was an exam. Okay, got it. Show of hands if you did it on Tuesday. That's not going to work. I can keep on and on and on and on. But in 2 weeks, we're all done. And then we are not really making any progress. Show of hands if you do act. Okay, fine, don't show hands. Think about it though. Do you go every day, go home, and actually do problems? If you're not doing what's expected and what's required for us to actually make progress. It's not all about biology. It's not all about English or math or whatever other class you're taking. It's about all of them. Show of hands if you're all going to transfer or go to a university in fall. Which one? UW? Western? Wazoo?
UW's,
Maybe
yeah.
out of state? To do a STEM, right? Maybe you're aiming to get a bachelor's in bio or biochem. You maybe want to go to med school someday or pharmacy school someday. Maybe you just want to do research someday. This is not the way to go. It's not going to be working. I could have understood last quarter. And it was okay. It was like, yep, this is new, this is hard. Okay, we are going to pick it up. But this is week 8 of second quarter. Show of hands if you would rather just get through Ochem with me writing stuff on the board and you go home and memorizing. I can do that. But this will be the most unpleasant experience you will ever have. Show of hands if you have actually come to see me during my office hours. Some of you have, but very few. Show of hands if once you get your quiz back, your exam back, you actually go through the whole thing and say, oh, I don't understand this. I need to go talk to Sunita about it.
Most of the time I do.
So just look around you guys. This is not a growth mindset. This is not a mindset where, yeah, this is tough, but she's there to help me. I need to go to her. Show of hands if you guys, and I know some of you guys did, met up and studied for hours before an exam. But that's not enough. That's not enough. If you're studying for hours the day before the exam, it's already too late.
Oh no, but also before.
Good.
No, no,
Perfect. Well,
not just
okay, I should have said only
Yeah.
there. That's not how higher level STEM classes work. Higher level STEM classes, no matter which field you want to go into, are not meant for, I'm going to marathon study the night before and I'm going to get it. The chances are you will not get it. It's about taking little every day, building it. But you have to do it every day. Sounds okay? Please, let's come back here. What will be the product if 2-butene were to undergo this reaction? Anybody? What is the reaction? What changes are we?
Hydration.
It's a hydration. Okay, we are adding water. Are we adding water Markovnikov or anti-Markovnikov?
Anti-Markovnikovs?
So where will OH go and where will H go?
H will go to the more substituted, OH will go to the
Use this example. Where will H go and where will OH go?
Since it's
They're the same.
Yeah.
One carbon is not more or less substituted than the other carbon. Isn't that right?
Mm-hmm.
So where will OH go? Well, it can go here or there. Okay. You might be like, but it's symmetrical. Yes, you're right, it's symmetrical. Okay, let's make it unsymmetrical. Does that change anything? OH can go here, but can't OH also go there?
Yeah.
Isn't that right?
Mm-hmm.
If the OH went here, let's say, this is an enol, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
1, 2, 3.
And OH went here.
Mm-hmm.
But can't the OH also go here? Is there any preference for one or the other?
No.
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 Both carbons are equally substituted. One carbon isn't more or less substituted than the other. Are you all seeing it? Now, will these survive? What did we say on Monday about enols?
Enols are unstable.
And what do they do when they are under acidic or basic conditions?
They
Tautomerize. So what will that become? If this tautomerizes, the mechanism of tautomerism must be known. What will this become?
and
Can it become an aldehyde? That's my question. What will this become, anybody? A ketone. What will this become? Also a ketone, just a different ketone.
Yeah.
So my original question
Two
was, can an internal alkyne, does everybody understand what I mean by internal alkyne?
triple bond in.
Can an internal alkyne give us an aldehyde?
No.
Not possible. Because both of those carbons are inside. Neither of those two carbons have hydrogen on them. You guys following that?
Yep.
So if I wanted to get an aldehyde, what kind of an alkyne must it be?
Terminal alkyne.
Otherwise, there is no selectivity. Exactly. Now, if I had a terminal alkyne, let's say for example, okay, not that. What will be the outcome for this reaction? Now I have difference, right? The two carbons are different. Now there is selectivity. One carbon of the alkyne is more substituted than the other carbon. Everybody sees that? So now we can actually get this or that because the carbons are different. So which direction would this go? Markov-Nikov or anti-Markov?
Anti-Markov-Nikov.
If it goes anti-Markov-Nikov, does it give me a ketone after tautomerism or aldehyde after tautomerism?
Aldehyde.
So what would that be? Anybody? 1, 2, 3.
1, 2, 3.
Isn't that right? Everybody okay?
Yes.
Everybody's seeing it? Because the O will go here. That's where the aldehyde will
4.
be. What if this were on the other hand being reacted with, is this going through Markov-Nikov or anti-Markov-Nikov?
Markov.
So where will the oxygen go? Will it go to the terminal carbon or the second carbon?
Second.
Because that's more substituted. So will that be a ketone or an aldehyde?
Ketone.
1, 2, 3, 1. Everybody okay? How do I know? Well, only the carbon that has a hydrogen can be an aldehyde because an aldehyde means this. If there isn't that, you can't get an aldehyde. Is everybody seeing that? Please practice the tautomerism mechanism. That comes a lot in your ACS standardized exam that we'll take next quarter. The tautomeric mechanism comes up a lot. Please practice that over and over again.
What's the meaning of tautomerism? You guys said it?
Tautomerism is an equilibrium process where the keto form is in equilibrium with its enol form.
Which explains why you drew the which is why you drew 2 arrows going opposite directions.
And in general, the keto form is more stable than the enol form. That's why the equilibrium favors that. That process is called tautomerism. It's not resonance. It is actually double bond moving, but an atom is also moving at the same time. This mechanism we should be able to write. It is either acid catalyzed or base catalyzed. It can happen in both. And then we also talked about a reaction today where ozonolysis of an alkyne gives us what?
Carboxylic acids.
Exactly. It breaks apart the triple bond and creates carboxylic acids where there were triple bonds. Did we talk about any other reaction that's actually useful? Reduction, hydration, and ozonolysis. Those are the main ones. And alkylation, basically converting this into a good even group, a good nucleophile and then alkylating.
And then putting it for SN2.
So that's kind of a summary for alkynes, guys. Questions? The expectation I have is everyone is spending 3 to 4 hours. Okay, fine, 2 to 4 hours every single day working on the problems. Because I'm giving you worksheets in class, on Canvas. The textbook has problems. That's my expectation. If we are not able to do that, then I don't know what else to say. Okay, I do have another worksheet though.
Oh,
Yes, please, go ahead.
well, I'll tell you over there. Some are not there, but some of.
Some are not there, some are.
But
Could
some-
you mark the ones that are not?
Okay, because there are some that are there and not here, but I'll mark.
Oh, there's some there. Maybe I'll just write it again and put it. Leave it, don't worry. I'll just write the key again for this and I'll post it. The whole thing.
Well, let me see, maybe this is there, because there's pages there that are not here, so.
Okay, I got it. Please take one pass. Please go ahead. Can you make sure everybody gets a copy? Alkynes doesn't have a lot of reactions. However, it is a very good place to start to do synthesis. Did everybody get a copy? Over there. Please pass it over there, Ali. Oh, okay. It's coming. I'll bring it there. Got it? Oh, am I short? How did that happen? Did you all get it? Oh, you all got it. Did you get one, Mark?
I don't know.
Yes, no, I don't know. Okay,
I-
you can use mine. So, please work through the, okay. Let's do a few together. How about we do a couple of them together? So, alkynes end up being a good place to start to do multi-step synthesis just because you can grow the chain so much. So, let's see. How about we do B, just because. So, the question says, starting with ethine, show how will you synthesize the following. Please note, they're not asking you for the mechanism. They're asking you for synthetic scheme. So ethine is this. How do I convert ethine into 1-phenyl pent-2-ine? What's the structure for 1-phenyl pent-2-ine? Anybody?
1-phenyl.
1-phenyl pent.
1, 2, 3.
And it's 2
4.
ions, so 2. 1, 2, 3, 4, 5. Did I draw that correctly? Yes?
Yes.
1.
Please don't take my outburst as an insult or anything
One,
to you. I understand
2,
being a student is not
3.
easy. You got too many things on your plate. I've been there, although decades ago. But the point is, you signed up for it, right? Therefore, it becomes our business, our job to do the best you can. If you think you are doing the best you can, then good, if that's your best. But if you see any room for improvement, well, then you gotta do that. Okay, so make suggestions, please. How do we go all the way from ethine to 1-phenyl pent-2-ine? Here's what I always suggest when dealing with questions such as this. Compare the two. When I compare the product to the reactant, can you see that this part of the product came from here?
Yep.
Everybody sees that?
Yep.
So what are we really doing? You're replacing one of the hydrogens with this.
With a benzyl.
And you're replacing the other hydrogen.
With an ethyl.
Isn't that right? How are we going to do that? You're alkylating an alkyne. You're putting an alkyl group on the alkyne. So how do we do that? Suggestions? Would the alkyne come as the electron rich part or the electron poor part? In this chapter, there's only one carbon-carbon bond making reaction we have learned. Only one reaction in this chapter which allows us to make a carbon-carbon bond. Which one is that? Not in this. There was no Grignard in this chapter.
Oh, there's no Grignard. Okay.
But Grignard can do that, although alkynes don't react with Grignard. What happens if I take sodium amine? What happens to the ethine?
Come to anion.
Exactly, right? That's a base, acid. The base takes a proton from the acid. It becomes, isn't that right?
Yeah, and then you.
Is that electron, is rich electron poor?
Electron rich.
So what do you think we need for second step? Electron rich substances can do two things. They can react either as a or as a so base or a nucleophile. What do we want this piece to react as to make the carbon-carbon bond? Do we want this piece to react as a base or a nucleophile? So what do we need then?
I just did an X substitute.
Say again?
I just substituted what would be the triple bond for an X. CO.
Wait,
So what did you use here?
added,
Benzyl with the chlorine attached.
You're going to do an SN2 reaction, which means that's going to be the nucleophile, so we need an electrophile that can do SN2 reaction. It can be any good leaving group, it doesn't have to be Cl, it could have been Br, it could have been OTS, any good leaving group, so you can do an SN2 reaction. You guys following? Yeah? Then what? That only allowed us to put one of the R's. What about the other R?
I did some more NH2.
And then?
ethyl brom.
Chloride, bromide, TS, any of the good leaving groups. Sequentially, you're basically deprotonating a terminal alkyne, putting an alkyl group, then deprotonating, putting another alkyl group. Does that make sense, everybody? Yes? Okay, that was way too easy. Let's do D. D. So once again, we are converting ethyne. It is the same starting material, same precursor. Have you heard of the word precursor before? Let me write it. Precursor means, you can take it, you can take it.
No, but I have it in writing there. For you.
I'll borrow it.
Okay. No,
Do you have this handout?
yeah, I have.
You can take it. I'll just look over. Don't worry. Precursor means something that you start with. So this is the precursor because you're starting the whole synthesis with this. Okay, so the same precursor, what is it being converted into, anybody? D.
Z66 dimethyl.
Go ahead, let's draw it out.
Okay.
Z66 dimethyl 1-phenyl hept2ene, right? Hept2ene. Say 1-phenyl hept2ene. Z.
1, 2,
1, 2, 3, 4.
1, 2, 3.
And was it 6,6 dimethyl?
Yeah, 6,6 dimethyl.
Did I draw this correctly?
Yes.
Okay. So how do we do this? Now, once again, can you see this piece in the product?
Yes.
Can you see this piece in the product? Yes? Where? Which part of the product is that
6,
piece?
7.
The double bond.
Do you all agree?
Yep.
Right? So now that will help us strategize. Okay, how do we do this? Suggestions?
And then
Okay. And then what?
H2 and Lindler's.
No,
No.
because what is that doing?
Oh,
That
that's
is-
that's deprotonating the alkyne. Okay.
So what would we need to do next?
a phenyl,
Not phenyl,
like
Benzyl.
benzyl. Benzyl what?
Benzyl halide or OTS.
So be specific. You're going to do an SN2 with one of them, right? Agree? Everybody okay? Okay, what do you think you should do next?
NH2.
Again, okay? Then what? So we've already attached this piece, right? What are we going to do now? We're going to attach this piece. Isn't that right? Is that what you're saying, Carrie?
I said T-butoxide, but it's not right.
No. T-butoxide is a base which can do elimination, E2. But do you agree?
Yes.
Another SN2, this is an SN2 reaction. We are doing a separate SN2 reaction with that electrophile. How many carbons? 1, 2.
4.
Did I do that right? 1, 2, 3, 4. 2, 3, 4. Yeah. So we now attach that piece. What do we have at this stage, by the way? What do we have after step 4? Do we have an alkene? We have an alkyne. 1, 2, 3, 4. That. Isn't that right?
Mm-hmm.
But we don't want the alkyne, we want that alkene. So what should we do next?
H2 and Lindlar's catalyst?
Now we can convert that into Z alkene because we want Z into, yeah, absolutely. Do you guys see that?
Mm-hmm.
Again, we are just taking all of the reactions we know step by step to get what we want. Okay, can we do F?
Is that E?
We can do E and F actually, we can do both.
Okay.
But you're right, I said F though. 1, 2, 3, 4, 5, 6, 7. Okay. We're converting alkyne, same alkyne, affine,
2,
into
4,
an
5, 6,
aldehyde.
7.
Oops, I'm missing us. Which, how
One.
many carbons in the aldehyde?
2,
7?
7. It's a 3
3,
methyl, right?
4, 5, 6, 7.
Yeah, three methyl.
Is
1,
this
2,
the
3, 4,
product
5,
given?
6, 7.
Yeah.
Yeah?
H.
Okay, cool. How? Suggestions? Ozonolysis of what, first of all? Sure, it's possible, but of what? What are we thinking? There are more than one ways of doing something. Right, so if we did ozonolysis of what, will we get an aldehyde? Okay, so one option is ozonolysis of an alkene. So how would you do that? Second, of this? Will it give, where will all the other carbons come from?
First, should we do the NH2?
Okay, you can do that. So if you're going to do
Sodium
that,
iodide.
what will you use for step 2?
I would use 1, 2, 3, 4, 5.
Lots of carbons.
Yeah.
1, 2, 3, 4, 5, 6, 7.
And that with a
1,
leaving.
2, 3, 4, 5, 6, 7 with a leaving group, right?
Yes.
Okay, then do what?
1, 2, 3, 4, 5, 6, 7.
Okay, there are multiple ways of doing, in this case there is more than one way of doing it. Yes, then what? Ooh. Ooh, would we need 7 carbons though? We already have, oh, I think they're thinking something else. You're thinking what I was thinking, but this will also, is this carbon, do you agree, is one of those?
Mm-hmm.
Oh, yeah, you're right. Count your carbons.
So do we need 7 then?
No.
1, 2, 3. Should we just have 6?
Mm-hmm.
Because that carbon is coming from here. Everybody okay?
Mhm.
Am I thinking right? I'm thinking aloud right now. I'm brainstorming. So if we did do that, what would we get?
You get that group attached to the alkyl. I think we need one last.
Is that right?
Yeah, I think we only need 5 carbons.
Because we
You're
get
thinking of a different synthesis, which is what I was thinking of.
Oh,
They're thinking of a different method.
okay.
We'll write that one too. We'll write that one too. So do you agree that if I did steps 1 and 2, we would get this?
yes.
And so now we have 1, 2, 3, 4, 5, 6, 7, 8, but we want only 7. And you were suggesting, Carrie, ozonolysis of an alkene, right?
Mm-hmm.
Can we convert an alkyne into an alkene?
Yes.
Yes.
Using what?
Lillard's capital.
Does it, in this case, does it matter whether the alkene is cis or trans?
No.
No.
So you can use either. You can either use hydrogen with Lindlar's catalyst, or you can use the dissolving metal one with sodium and liquid ammonia. Either is fine because there is no E or Z there. Everybody okay?
Mm-hmm.
So if we do that, we would get
an alkene.
Right. 2, 3, 4, 5, 6, 7, 8. Do you all agree? And Kerry was suggesting, well, let's
one,
do
two,
ozonolysis
3,
of that.
4, 5, 6.
Ozonolysis of that, which will break right there. We are not interested in that part, but this part will give us the product. Make sense, everybody? Yes? You are thinking of a different way of doing the synthesis. Fine. What would that be? Sorry, what were you saying, Kevin?
I was gonna say, is this like a more complicated way of doing it, or
No.
use more
No.
resources? or-
Actually, you'll notice it's about the same for the other one as well. But how else can I get an aldehyde from an alkyne? Ozonolysis absolutely is one way. What other reaction gives us an aldehyde from an alkyne? Louder? Hydration? Yes, absolutely. Hydration. If I did a hydration of an alkyne, we can get an aldehyde after the tautomerism, right? So
Go
do
for the
we want?
enol.
So let's picture this, okay? In that case, are we trying to do Markovnikov hydration or anti-Markovnikov hydration? Do you all
Anti-Markovnikov.
agree?
Yeah.
And I think that's what you guys were thinking. If it's going to be anti-Markovnikov hydration, where is the alkyne? Isn't the alkyne going to be there? Isn't that right?
Yeah, it
So
could be
both
there.
of those carbons are part of alkyne. Those two carbons are coming from here. Agreed? So how many more do we need to bring in? 1, 2, 3, 4, 5.
We would need to bring in about 3 more carbons.
5.
5 more.
Agreed?
5 more carbons.
I
Okay.
think that's what you guys were thinking. And that's what I was thinking earlier, but then when Kerry mentioned ozonolysis, I was like, yep, that's possible as well. And then, what do we do? So now, at the end of step 2, we will have, after step 2 is done, 1, 2, 3, 4, 5, we would have this. Am I right?
That's after step.
After step 2. Agreed? So what do I need to do to this guy to make it into the aldehyde?
Ozone and BH3 and BH3 and hydrogen peroxide.
Totally fine. As long as you're able to see those sequences, totally fine. Sounds okay? Everybody? Of course, there are more examples on this worksheet. Must work through all of them. All of them. Let's try one more. Let's do on the bottom of the page. Which one will be funner?
More interesting.
No, funner. There's no
The funner, the
Um,
funner.
Converting
funner, funnest.
acetylene
Difficult.
to an alkane. A cyclone.
Okay, so let's do this, the middle of the page, B. Would someone let me know if the key for these two worksheets are on Canvas? When you go home, you can let me know, send me an email or something.
I
Oh,
told you that.
this is not, this whole thing is, oh, you
All of
made
this
it.
is
I
just,
see,
yeah.
I see what you're saying, I see.
Those two are not in camp.
Okay, then I will write those down. Okay, how do we turn 1-bromo, 1-methyl cyclopentane? Into that product. How do we turn that reactant into this product? Why don't you guys take 5 minutes, brainstorm, and decide. You can use any of the reactions we've learned so far. Don't be afraid to combine chapters because they are all part of a big picture.
So,
Yes.
yeah, okay. I put here like
This is not in Canvas, yeah, so I will.
Not in
Yeah,
Canvas.
this
and
page
then
I
this
need.
is in Canvas.
Is there any pages in here that are not?
This is in Canvas. This is in Canvas. And here's I'm missing after this. I'm missing page that's in Canvas, not here.
Oh,
And it starts like this.
oh, okay.
Starts like that.
Okay.
And then this is in Canvas,
Okay.
and this is
Not
not in
in Canvas,
Canvas.
okay.
It's not here either, right?
Okay, I'll work on
And
this.
then this one,
I
oh,
have
this
a-
one is in Canvas. Yeah. So, yeah.
Here's a copy for you. Okay, I'll work on these.
So
I-
we get these, but we also get that one, right?
Yes, I know.
You don't have a copy of that?
I
can
have
go
it
upstairs.
upstairs.
I can go upstairs.
I have it upstairs. And I can quickly make a copy and,
Yeah, I'll go get it upstairs.
okay, thank you. Ideas?
Would you start with, doing, using RO minus for Hoffman's product?
Be very specific.
I used
OT.
OKO-butyl
T-butyl?
T-butyl.
But if you use T-butyl, okay, if you use T-butyl oxide, what will be the major product? I'm assuming you're doing E2, dehydrohalogenation. Is that bulky or small?
Bulky.
So will that give you Zexef's alkene or Hoffman's
Hoffman.
alkene?
Hoffman's
So
alkene.
what will be the major product from here if we use that?
Sorry, I was looking at the first one. I
Oh,
wasn't looking
then
at this one.
absolutely.
Okay.
Yes, the first one absolutely.
So instead of butyl, can you just do like NaOET?
Okay, good, a small base, right? Because if you use a small base, with heat, yes, absolutely.
Sodium ethoxide.
You would get that. Is that what you want?
Yeah.
Okay, what can we do next? Good, very good.
I did HBr with the peroxide.
Because why? You're trying to get a BR here. Is that right?
Yeah.
Okay, so if we use HBr with peroxide, this will put a anti-Markovnikov hydrobromination, so put a BR here. Is that right? Why is that helpful? Because now it gives you somehow to bring in something else here, because you have a leaving group. Everybody's seeing that? Okay, what will we do next? Very good, yeah,
Could I
absolutely.
use Grignards or whatever?
Grignards, what will the Grignard do?
Make a good nucleophile out of the.
Oh, you want this to be a Grignard?
Huh?
Huh?
Huh? I thought that was to make the branch a nucleophile at the end of the double bond.
So you want this to be the nucleophile,
Yeah.
this part to be the nucleophile.
And then I wanted to replace the BR.
Oh, I see. You want the Grignard to be the nucleophile to do SN2. Grignards don't generally, when you remember SN1, SN2 when we studied, Grignards were nowhere in the picture. Grignards came in the picture when you were dealing with epoxides because there's an oxygen there. We will see it in alcohol chapter because there's an oxygen there. Grignards do not do SN1, SN2 in the normal manner. But you do have an idea there that, hey, we could probably bring in a nucleophile that takes the place of the Br. What would that nucleophile be?
Would it be C triple bond CR?
We are in the alkyne chapter. Where's your alkyne? Right? 1, 2, 3, 4. 1, 2, 3. That's a nucleophile, isn't it?
Yep.
That's a nucleophile. Okay, what will that create once SN2 has happened? 1, 2, 3, 4. Am I right?
And since it's
And
a
then?
cis alkene, we use H2 in Lindlar's catalyst.
That's a cis alkene, that's a Z alkene. So once you've done step 3, you can do hydrogenation with Lindlar's catalyst to give us the cis alkene. Yes?
Would there, and this is just my thought process.
Yeah, yeah.
Is there a way to remove the bromine from the first thing and then somehow have like a positive charge on like
But that's a mechanism you're saying. Can it make a carbocation to do something? Sure. What's the nucleophile you're going to put on it? So, mechanism tells us how do I go from here to there? Or how do I go from here to here? Or from here to here, so on and so forth. Synthetic scheme is telling us, well, we can use this to convert this into that. Mechanism is not being discussed here. We can use this to convert that into this, so on and so forth. So, can this make a carbocation? Absolutely, but then what are you putting in its place to help us go in that direction? That's the question. Does that make sense what I'm trying to say?
yeah, it makes sense. I'm having a really hard time remembering what you
Yeah.
do.
Yeah, and that's why that's the tool I use, is that reaction map kind of thing to visualize. The other is practicing. If you practice one of these reactions 20 times, then hopefully 21st time you automatically remember because you've seen it 20 times before. That's what practice is all about. Everybody okay? Yes? Okay, homework. This time I will collect it on a piece of paper. So on Monday, please give it to me. So do this on a piece of paper. Give it to me. Using, that's not using, using styrene and, okay, wait. Isobutane and acetylene as your only carbon source. Give me a second. Okay, please understand the question though. I want to make this
One,
compound.
2, 3.
You can use any reagent,
Four.
but carbons must come from these 3 choices only. You can use any
1, 2,
reagent,
3, 4,
but carbons must come
5,
from
6.
those 3 substances only. Does that make sense?
Mhm.
Yes? Thursday, Friday, Saturday, Sunday, Monday, I need it on a piece of paper. Everybody okay?
Mhm.
Cool. Not asking for mechanism, that's not the question. I'm asking for synthesis. Okay. Let's go on to the alcohol chapter. That's our next chapter, chapter number 17, because we did NMR-IR already. So chapter 17, alcohol and phenols, is our next chapter. Can someone tell me what is an alcohol
OH.
a hydrocarbon with an OH on it.
and what's a phenol?
Benzene with an OH on it.
Phenol is basically when the OH is on the benzene ring, that's a phenol. Alcohol is when the OH is on an sp3 hybridized carbon. Okay, those are alcohols. We typically write alcohols as ROH. Agreed?
Mhm.
Now, there are three kinds of alcohols. I'm going to save phenols for later. Actually, we won't do too much phenols in this chapter. We'll do phenols much later in the quarter, probably next quarter. So we are focusing on alcohols right now. There are three kinds of alcohols: primary alcohols, tertiary secondary alcohols, and tertiary alcohols. Do you guys remember that?
Yes.
What are primary alcohols?
Hydrogens on,
Say again?
hydrogens on the.
How many?
All of.
All of them?
Oh no, no,
Two.
one, two and one.
Two. So there's something.
There's an RCH2OH.
What's a secondary alcohol?
2 R's.
2 R's, 1 H, which can be the same or not. What's a tertiary alcohol?
1 R.
No H's, only R's. On the carbinol carbon. This carbon, by the way, the carbon that has the OH on it is called the carbinol. So depending on the substitution of the carbon, you can designate the alcohol as being primary, secondary, or tertiary. What's the hybridization state of the oxygen? Can I erase this? Everybody got this?
Yes.
I didn't, so hopefully somebody got this because I don't remember what I said. Send me a picture. Thank you. Okay. What's the hybridization state of the oxygen atom?
SP3.
sp3. So what's the shape at the oxygen atom?
Bent.
Do you all agree? Everyone okay? Just like water. Alcohols and water behave very, very similarly because their structures are very, very similar. Water, if you remember, has a bent shape according to Vesper. Alcohols have the same. The only difference between the two is that alcohols have one of the H's on water substituted with R. Everything else is the same. Do you consider water to be a strong acid or a weak acid?
Weak acid.
Same. Do you consider water to be a strong base or a weak base?
Strong base.
Really?
Yeah, weak
Can
base.
can water deprotonate a weak acid?
No, weak base then.
So then same here. Very weak acid, very weak base. Very, very similar to each other because their structures are very similar. Is water polar? In whose direction?
Oxygen.
So is alcohol. Of course, in alcohol it also depends on how big the R is because R is the non-polar portion. But at this side, yes, absolutely, oxygen is pulling electron density towards itself because oxygen is more electronegative. So very similar things between the two. Everybody okay? Yes? Okay, let's talk about IUPAC naming of alcohols. Only alcohols, not phenols right now. We're only focusing on alcohols. Now, alcohols in IUPAC are not called alcohols. IUPAC calls them alk. We all know what that means?
Yeah.
Right?
Number of carbons
In
on the
water.
parachain.
And oils.
Alkanols?
There is no E there because these are not hydrocarbons anymore. There's a heteroatom. There's oxygen in there. Right? Alcohols in IUPAC are alkanols. So let's look at each piece. What does alk tell us?
Number of carbons in the parent chain.
So what is the parent for an alcohol? The parent for an alcohol is the longest carbon chain containing the OH. The OH has the highest priority. So far. We are going in the increasing direction of increasing priority. So of everything we've studied so far, alcohol is the highest priority. So the parent must have the OH in it. And which also means that the carbonyl carbon, the carbon that the OH is bonded to, must get the lowest position possible. So when you're numbering your parent chain, you have to number it in such a way that the carbonyl carbon, the carbon the OH is bonded to, gets the smallest position number. Okay, what does this tell us? What is sp3?
sp3 hybridized carbon.
So that's telling us that all the carbons are sp3 hybridized, right? What is that telling us essentially? That all carbons are carbon-carbon single bonds. Isn't that right?
Yep.
Because if a carbon were sp2 hybridized, what bond will it be making?
An ene.
So if, let's say, we look at examples, if there were carbon-carbon double bond in the parent as well, what will this be replaced with?
En.
Exactly. En. No E at the end because it's not a hydrocarbon. If there were a carbon-carbon triple bond in the parent, what would that be replaced with?
Ein.
Make sense? Should we give the position of the all?
Yes.
Absolutely, because if it's possible for it to be in different places, then yes. And R and S, stereochemistry always comes first. R, S, E, Z, whatever that might be. Everybody okay? Now, if it were an alcohol attached to a cycloalkane, not benzene, that's not a cycloalkane, then those are called cycloalk, as you would expect. Once again, the same thing. The parent, AN, if only carbon-carbon single bond. If there were a double bond, then E and YN, if there were a triple bond in the ring somehow, and all at the end. Sounds okay, everybody? Okay, let's try a few.
Do we have like,
Sorry, what?
like, oh yeah, you did say it, right? 1, 2 En, for example.
So
Like if we had 3, 4 En.
yeah, then you change
Same thing.
whichever parts need to, and we'll do some examples to see. I thought I brought my notes with me. I have to think. Oh, come on. Okay, let's draw. Oh, one more thing, sorry, one more thing. We learned last time that if there's more than one ene or more than one ein, what do we do? A,
Alka, tri.
and then diene, triene, down.
We do
What if there's
trial.
more than one of all?
Diol,
Good.
trial.
But then,
Trial.
yes, diol, triol,
Tetra?
tetrol, whatever.
Cycloalka.
But in that case, yes,
Cycloalka trial.
yes. But in that case, we keep an E over there. For polyols, if there is more than one alcohol, then we keep the E at the end. Okay? And I'll try and make sure I draw examples of all different kinds. Oh, is this okay, Tanya? Is that too far? Okay. Okay, let's try these. Ready?
I have a question.
Oh, question, sorry.
As far as,
Yes.
where do we put the number
Of what?
of where the alcohol is?
Yes,
And
if
where-
it matters.
Do we put it before?
Right where the alcohol
One,
is.
two.
Or we?
That's why we broke it up into pieces. If you need to put a number, you put it right before. If you need to put a number, you put it right before. Let's try it out and see if your question gets answered. Okay?
Are we
So, yeah, question?
No, I thought we were gonna pass.
Okay, let's try this. First job is to pick the parent, right?
Yeah.
What's the parent? The parent must contain the OH because that has the highest priority.
Mhm.
The longest chain that contains the OH. What would that be in this case?
Hexanol.
6 carbons. Because here's your OH 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Why?
Because
More branches.
More branches. If you have more than one possible parent chain of the same size, then the one with more branches. Do you all agree?
Yes.
Yep.
And then which direction should I number this from? Closer to the OH or closer to the 2 methyls?
OH.
Exactly, because that's the parent that has the highest priority. Absolutely. 3, 4. Do you all agree?
Mhm.
Is there any stereochemistry shown here?
No.
So
No.
we don't need to worry about it. Let's start with the groups. Alphabetical order, as you would expect. Go ahead.
3 benzyl.
There's no benzyl. It's phenol. There's no CH2 in between.
Free phenol.
Right? So who comes first?
4 ethyl.
There's no ethyl. Oh, there is an ethyl. Bah, sorry. There is an ethyl. My mistake. Absolutely. Then what?
5,5,9,9.
5,5 dimethyl, okay.
3-phenyl.
Sorry, louder.
3-phenyl.
3-phenyl. And then, so your groups are done, right?
Yeah.
Now comes the parent. So what's the alk over there?
Hex.
Is there a double bond or a triple bond in the parent?
No.
So, right? And now where is the all? So I think this is what you were asking, Carrie. Where is the all? It's
Carbon
on
2. Hex and 2
Oh,
off.
so you put it after the hex.
Before the piece, this is the all piece, alcohol. This is the OH, so before that.
Okay.
This is the enorine, so before that. Make sense?
I didn't know if it was like, it would be 3-phenyl 2-hexanol or like 3.
So that is an old way of doing things. The new way, which is what I think is the best way, because what if you have this? Then that way doesn't work.
Yeah.
So yes, let's just put it right before that piece in the name. Removes all confusions. Okay, does that okay? Sound okay?
Mm-hmm.
Okay, next one. What is the parent?
Cyclohexane.
Okay, cyclohexanol. with the
Cyclohexanol.
alcohol. Okay, is there stereochemistry?
Yes.
What is that?
1s3s.
There's no wedges, dashes. You can't assume that any of, unless they're shown that way, we can't assume whether these are wedges or dashes.
Cis and trans.
All you can do is cis and trans. You can't do RRS unless wedges and dashes are shown. Does that make sense, Jane?
Yeah, that makes sense.
So what is this? Is it cis or trans?
Trans.
Okay. Group. Where's carbon 1, by the way, in the parent? Where should be the 1? Carbon 1.
OH.
Has to be the carbonyl carbon. You have to start from there.
Mm-hmm.
Highest priority. Everybody good?
Mm-hmm.
Okay, group. So where is this guy? 1, 2, 3. Chloro. Agree?
Mm-hmm.
Now the parent. So what's the parent? Cyclohex. And because there's no double bond in there, and all. Now in this example, do I need to say one all? Why not? It's implied because it's a ring. And there is only one all, so it's implied that it's going, you have to start from there no matter what. There's no other place we could start counting from in that structure. Yes, Viola?
But can we still do it if it's
You
a
can
KZ?
still do it. Absolutely, you can do it. You can still call it cyclohexane 1 all. Totally fine.
Uh-huh.
Make sense, everybody?
Mm-hmm.
Good with that? Okay, let's try this. Is there stereochemistry?
Yes.
Why don't we go ahead and figure out what that should be?
2s.
Where is the 2 though? Where did we start
Oh.
numbering from? Did we start from left or right?
Left.
Why left?
Because
Left.
it's the shorter version as opposed to the other side. It would be one longer.
What does that mean, short or longer?
1, 2, 3, 4, 5, 6,
4,
7.
5, 6, 7. Oh, when you're saying shorter version, you mean the thing hanging off the triple bond?
Yeah.
Okay, so the point you're trying to, okay, so first thing is, guys, first thing you got to decide that the OHs get the smallest position. That's the priority number 1, because that OH is the highest priority group, right? Now in this example, the OHs are on the same positions. It wouldn't matter whether it's 1, 2, 3, 4, 5, 6 or 2, 6, it's the same. Everybody agrees?
Mm-hmm.
So if that were not the same, OHs get priority, period. Because the OHs are along the same positions from either direction, then the triple bond gets looked at to give it the smaller position number. Make sense, everyone? Yes? So absolutely, in this case, only because the OHs are equidistant from both ends, am I going to then give the alkyne the smaller number. Did I number 1, 2, 3, 4, 5, 6, 7?
Yeah.
Everyone okay?
Mhm.
Okay, so which one did you say is S?
Both.
Both for us.
Oh, they are both, okay. 1, 2, 3. Okay. Yep. Okay, so we are ready to name. Go ahead.
2s,
2s,
6x,
6s,
hept dash 3 dash ein.
hept, good. 3, ein, but no e there.
Yeah.
No, should there be e there?
Yeah.
Because there are 2 alcohols. Because there are 2 alcohols, we are leaving that e there. Absolutely. Only because there are 2 alcohols. And then comes what?
Dash 2
2,6 dial.
6 dash dial.
Got it? Everybody agrees?
More than one alcohol with
Exactly.
number before the and means.
Exactly. Exactly.
No.
Everyone okay?
Yes.
What if the OHs were not equidistant from both ends? Like in this case, it ended up being, even though I didn't mean it to, but what if they were not equidistant from both ends and it were, let's say, okay, no, don't do that. But then I can't do that.
Make it longer.
Yeah, okay, good, yeah, but, come on, fine, whatever.
1,
Okay.
2. This side, you start on the left.
I brain's not working. But what would the name be? So again, the OHs get priority, not, oh, I see what you mean, I see what you mean. There we go. Yeah, that should be it. The OHs get priority first. So which direction will we number the
Left to
pen
right.
change from?
Left,
The left, so you can get a small.
Left to right?
right to left.
Choose one, pick one.
Left to right.
Right to left because you'll be counting from the OH on
You
carbon
start
1
one
if you
over
count right to
1,
left.
2, 3, 4, 5, 6, 7. So that is OH gets priority. That's 2, 7. Or 1, 2, 3, 4, 5, 6, 7. Which
Two,
is
one,
1
si-
and 6.
One,
Which is better for
Left
One,
OH?
to
six.
right.
2, 7.
Right to left.
1, 6.
From here to there?
I mean, right
Yep.
to left.
That's
yeah.
right. The other right to left?
No, I did.
The red.
Didn't I say?
Yeah, the
I
red.
said left to right. That's okay.
Ah,
The red
well,
one,
I
right?
meant
I mean this.
I meant left to right, which is wrong.
But this is what you meant, right?
Yeah, that's what I meant. Which is mine.
So then what would the name be? If that were the case, what would the name be?
Wait.
Hept? Is it still hept? Right.
So after that.
1, 2,
Four.
3, 4, 5, 6, 7, yeah.
Dash
4,
4
ein,
ein with an E.
with an E.
Yeah, with an E. Dash 1 6 dial.
Do you all agree?
Yes.
The point I'm trying to make is, first your job is to give this the lower number. If that is going to be the same no matter what, then you look at the double bond or the triple bond. If that is going to be the same no matter what, then we look at the groups, if that makes any difference. Okay, I know we are almost getting out of time, so let's run these three very quickly, guys.
I got
So,
that.
what's the parent?
1, 2,
Or
non.
4,
So do
5,
you
6,
agree?
7,
1,
8.
2, 3, 4, 5, 6, 7, 8?
Oh,
Yes. Did I number those correctly?
Correct.
Okay, let's start. Is there easy?
Yes.
Yes.
What is it?
Easy.
2E 4Z.
2E, this is E?
Yeah.
Yep.
And
Z.
Z. Okay. So you're saying 2E, 4Z,
Yes.
okay?
4
Mm-hmm.
4
5.
6. Sorry, 4 5 6 trimethyl.
Oh, really?
No, it's an ethyl.
There's an
5,
oh,
5,
5 ethyl.
Right,
I wrote down
that's okay. 5 ethyl,
4, 6 dimethyl.
4, 6 dimethyl.
And then
4
2, 4,
dimethyl
non
octa.
in.
No,
I mean oct.
no.
Octa.
2, 4, does that go with the ene?
Yes.
So then put it with the ene. Oct,
Also oct
2,
backwards.
4,
Yeah.
oops, 2, 4.
2, 4.
Diene. So what should I do if there is more than one ene or ein?
Octa.
E.
Octa.
Oh, octa.
The E
Yes.
is if there's more than one all.
Okay.
Is there more than one all?
Yes.
There's
Is there
no-
more than
there-
one all in this?
There's
No.
one all.
So
So
what if
should
you
I
have?
use an E?
No.
No, I think I have an example of that as well.
Yeah. No.
And then what comes next?
One all.
Can we put the one or not, or we have to?
We should. Cycloalkanes, it is, cycloalkanols, it is assumed that it should be one, but alkane, it's not always assumed. That you should. Okay, quickly, how about this guy? I know we are out of time, so can we very quickly do this?
3 isopropyl.
Is there cis and trans?
Trans.
There's
It
trans.
is visible because notice how this is straight up and this is straight down, there's no ambiguity. So if the structure shows, we must include it. If this were not as clear, then that's a different story, but that's pretty clear, up and this is down. Okay, trans what?
3 isopropyl.
Isopropyl, okay. Say again? Cyclo?
Pentanol.
Heptanol?
Pentanol.
Pentanol. I am hearing things like. Everybody agrees? Now here we don't have to say one all because for cyclo ones it's assumed you started from there. Last one. Last
Oh, I'm
one.
holding it.
Sorry? Oh, come on, one more.
I got rehearsal.
Rehearsal for what?
My show.
What show?
Into the Woods musical.
When? Where? Invite us.
It's Arlington High School, and it's this Friday.
Folklore.
Very cool. Folkloro.
Can we indicate E or Z?
Good. Should it be E or Z? Can this be E or Z?
No.
No, but this one can. Is it E or Z? It is Z. That's priority 1, priority 2. This is priority 1, hydrogen is priority 2. It is Z. Absolutely. Okay, Z for chloro what? 1, 2, 3, 4, 5, 6, 7. Don't we have methyl? 6 methyl. And then comes hepta. And 4, 6. What? Diene. But then there are 2 alls.
E.
Dieno.
E.
Right?
And then 1, 3.
That's for those. This is for the alls. 1,
1, 3.
3.
Die. Oh. Die. Die.
His name is big enough.
Oh, they're going to get funner. Funner. Look at ethers, aromatics. It all starts coming together. But again, you got to go piece by piece. Start adding. Okay.
Ouch.
For the exams, do you want us to just redo all of it? if we're
No,
gonna
just
do it,
the
or
things that are wrong.
Just the ones that we missed?
Yes.
We can leave the other ones.
That's,
right?
yes, and just that's why I'm saying give them both to me so I can compare them.
So redo the questions we got wrong.
Yes,
Okay. Thank you, Samita.
yes.